Hello, this is the fifth part of my lecture on the physicalists, and today I want to talk about Hermann-von-Helmholtz and Franciscus-Donders. Helmholtz was one of the great figures of 19th century physics, but also devoted much attention to physiological investigations. Born in 1821, he grew up in the Prussian city of Potsdam. Poor, but exceptionally gifted at his schoolwork, he agreed to serve as a future army surgeon in exchange for a free medical education. Studying in Berlin, Helmholtz came under the influence of the great physiologist Johannes Müller, and befriended a number of his students, including Émile Dubois-Reymond, himself later to become famous as the pioneer of electrophysiology and the discoverer of the action potential in nerve cells. In 1845, Müller's former students and others, including Helmholtz, formed themselves into the Berliner Physikalische Gesellschaft, the Berlin Physical Society, to further their shared interests. Fundamental to the group was the view that all phenomena, including neural and mental processes, could be accounted for in terms of physical principles. Dubois-Reymond had earlier stated the mechanist doctrine that was common to the group's members: no forces other than the common physical-chemical ones are active within the organism. Rejecting Müller's vitalism, they set about establishing how these forces worked. Helmholtz soon gained fame for an 1847 paper on the conservation of force, in which he directly rebutted the vitalist views then still prevalent amongst many biologists and physiologists. For the vitalists, the processes of life were partly powered by an immaterial and imperceptible vital force that was present in all living things. In effect, a latter-day version of the concept of spirit. Helmholtz addressed this question in studies in which he measured the amount of heat produced by a frog's body and was able to account for it entirely in terms of the oxidization of its food. That is, the total energy involved in organic processes was constant, just as in physics, where all machines obeyed the law of the conservation of energy. There was no more a vital energy in biology than there was perpetual motion in physics. The physiological processes that Helmholtz studied followed mechanistic principles, and the underlying unity of biology and physics was demonstrated. Helmholtz's conservation paper so impressed the Prussian government that he was excused further military service and was made lecturer of anatomy at the Berlin Academy of Arts, and a year later professor of physiology at the University of Königsberg. Thereafter he occupied a variety of academic posts in physiology and later in physics, coming to be regarded as one of the preeminent scientists of Europe, in recognition of which he was later ennobled by the Prussian state, so coming to be called Hermann-von-Helmholtz. He died in 1894 at the age of 73. A complete summary of his scientific and philosophical work would require a much longer video, and I will here only briefly summarize some of his main findings relating to psychology. In the 1840s, Helmholtz investigated the speed of nerve impulses. Following Galvani's discovery of the electrical nature of nerve impulses, most physiologists had come to see the nervous system as similar to a set of electrical wires through which current flowed. This led them to believe that neural transmission was very fast. However, studies of nerve fibers by Dubois-Reymond suggested that the impulse might be electrical-chemical in nature rather than purely electrical, in which case it would be relatively slow. Helmholtz then devised experiments to measure the speed of transmission as best he could, finding that it was relatively slow and that the prevailing consensus was therefore wrong. This work led to further studies in the timing of reaction times and mental acts, thus demonstrating that at least some mental processes could be measured, a development which can be seen as a major breakthrough in the history of psychology. During the 1850s, Helmholtz studied color vision. There was as yet no clear understanding of how people were able to perceive color. Newton had established that white light from the sun was a mixture of light from all visible colors, but how did the eye and mind perceive them? Building on earlier ideas by the English polymath Thomas Young, Helmholtz hypothesized that just as physics identified three primary colors, which form the other colors by combination, so the human retina must therefore have three different kinds of receptor cells, each furnished with a chemical sensitive to one of the primary colors. He then provided empirical evidence for what became known as the trichromatic or Young-Helmholtz theory of color vision. He also examined the color of afterimages and the phenomenon of color blindness. This was a testable, mechanistic explanation of how the brain perceived color, firmly established link by link, and led to all of the old speculations being discarded. Helmholtz's work on color vision was part of a comprehensive and prolonged inquiry into visual perception, which led to the publication of his great Handbook of Physiological Optics, which summarized all the research that was then available in 500,000 words, and became the standard authority for several generations. He also found time to invent the ophthalmoscope, a revolutionary development in medical technology which enabled doctors to view the living retina for the first time. Again, Helmholtz established the modern distinction between sensations and perception, for example, between the images received by the retina and transmitted by the optic nerve, and how the mind interprets the arriving impulses. Helmholtz's empirical investigations were undergirded by an awareness of the philosophical issues involved. Thus, in response to the old question of whether or not we actually see what is really out there, a question that had been addressed by Democritus, Berkeley, Hume, amongst others, Helmholtz was dismissive. We have to accept that our ideas of things can only be symbols, but we can only talk about them in practical terms. In practice, we learn how to use these symbols in order to regulate our movements and actions, and so bring about our desired results. For example, the sensation of red is the normal reaction of normally formed eyes to a particular form of reflected light. If all physically normal people see the same color as red, then it's pointless to ask if what we see is really red or a sensory illusion. In terms of epistemology, Helmholtz agreed with Kant that sensations are interpreted and given meaning by the mind, but he disagreed that the mind innately possesses categories and intuitions to supply those meanings. Rather, the categories are built up through a trial and error process of learning which reactions to a visual sensation produce an expected result and which don't. Space perception is a case in point. Kant had said that the mind innately intuits spatial relationships, but Helmholtz argued that we learn about space through unconscious inference. As infants, we gradually learn to make correct spatial judgments, so that clues of size, direction, and intensity of hue lead to the perception of distance and the relative placement of objects. The British empiricist associationists had said much the same, but they lacked the experimental evidence to back it up. As a thoroughgoing experimentalist, Helmholtz supported his theory with research findings. Thus, he constructed eyeglasses with prismatic lenses which distorted vision, so that when subjects first wore the glasses, they were unable to touch the objects in front of them. Then, after their perception had become adjusted to the new sensory data, the removal of the glasses led to a second period of an inability to touch objects. In both cases, the subjects' minds had to reinterpret the messages received from the optic nerves before they could function in the new sensory environment. Finally, let me turn briefly to Franciscus-Donders. Donders was a Dutch ophthalmologist who responded to Helmholtz's study of the speed of neural transmission with an ingenious experiment of his own, which must rank as one of the most significant in the early history of psychology. He speculated that as nerve impulses take time, then higher mental processes probably do so too. His experiment consisted of three parts. First, to get subjects to consciously react to hearing a single nonsense sound by repeating the sound as quickly as they could. Then, to get subjects to consciously react to hearing a series of different nonsense sounds by repeating the sounds as quickly as they could, that is, requiring them to discriminate between sounds. And lastly, to get subjects to consciously react to hearing only one of several nonsense sounds by repeating the sound, that is, requiring them to both discriminate and choose between sounds. All responses were timed, and Donders found that the average time of response varied. Thus, discrimination took an average of 39 milliseconds more than simple reaction time, and choice took an additional 36 milliseconds. Donders had shown that thinking takes time, and that unseen psychological processes could be investigated using elapsed time. Higher mental powers could be measured.